Assalamualaikum and good evening. I bid to all of my fellow judges and all of my fellow friends. I am NURULSYAZWANI binti MUEEDIN as the first presenter to present to you about our production of 30,000 metric tons of 1-propanol per year. I will explain roughly about our process flow in design project 2, which is we start our DP2 with process integration and then followed by process control and instrumentation, and then we start our design of major equipment individually, which are consist of heat exchanger, hydroformylation reactor, two-phase separator, hydrogenation reactor, and distillation column. And then we will explain a little bit about our economic analysis, and lastly our plant safety and layout. So I will pass to you to our next presenter to explain more about process integration. Thank you.
Assalamualaikum and hi, I am KAMALINA AZYYATI KAMARUZAMAN. Today I will be presenting chapter 7, process integration. Process integration is a typical method used in industrial process to minimize the utilities consumption. To apply the pitch technology analysis, several steps must be followed. The first step is we need to identify the hot, cool, and utility stream before extract the data from process flow diagram. Then we need to construct problem table algorithm P3A to determine the energy target and pitch temperature. Lastly, we need to design heat exchanger network (HEN) to calculate the minimum number of heat exchanger required. So this is the thermal data extraction from PFD and delta H from energy balance. There are 5 heater and 1 cooler that are being considered for pitch technology analysis. The boiler and condenser are not be considered because it will affect the stability of the plant. After that, problem table algorithm PTA will be calculated to determine the heat surplus and deficit within the temperature interval. The delta timing used in this PTA is 10 degrees C, where the conservative temperature will be 5 degrees C. At the end of the PTA, the energy surplus are cascading down within the temperature interval from one temperature to the next. Since the cascade heat flow are all in positive value, no further calculation are required. Based on the calculation, the pitch occur at temperature 607.63 degrees C. Hence, the temperature pitch hot is 607.63 degrees C. The temperature pitch cool is 602.63 degrees C. The QH min is 0 kilowatt and the QC min is 9,538.67 kilowatt. Thus, we conclude that this plant experience threshold problem since there is only QC min required for this process plant. After that, heat exchanger network (HEN) is designed to achieve the energy target by PTA. It is represented in a grid diagram as the diagram shows the heat transfer and pitch temperature clearly. From the HEN design, we can see that the heat is integrated between stream number 1 and stream number 5, and there are 5 cold utilities on the hot stream where the heat load is same as the QC min calculated in PTA. The TH diagram was plotted to determine whether the heat exchanger are feasible or not on that stream. Hence, the heat exchanger is feasible because the delta T for hot and cool stream are greater than delta T min and both streams did not cross each other. Then, the comparison between the hot utilities and cold utilities are being made. Before the heat integration, the heat load required for the hot utilities is 161.05 kilowatt and after heat integration is 0 kilowatt. So the percent saving is 100% for the heat load required and for the cost utilities. Then the heat load required by the cold utilities before the heat integration is 9,699.72 kilowatt and after the heat integration, the heat required by the cold utilities is 9,538.67 kilowatt. The percent saving is 1.32% and 1.65% for the heat load required and cost utilities. Thus, we conclude to proceed with heat integration for this plant. As we can see, 100% for the hot utilities and 1.65% for the cold utilities.
Hi, I am Jimmy and let's move on to Chapter 8, Process Control and Instrumentation. A brief intro for PNID. PNID is a diagram that consists process equipment, piping, and instrumentation control device. Stated in the slide is our control system that we implemented in our plant, which is feedback control, feed-forward control, ratio control, and selective control. These controls are simple compared to cascade and concurrent control system, but these also depend on the operator itself. Shown in the slide is a PNID of a heater. The objective of the control is to monitor the temperature of the outlet stream. So what we do, we implement feedback control. And what we manipulate is the heating duty of the heat exchanger. Move forward. This is the simple PNID for distillation column, whereby all the control system is feedback, but there also down there which is cascade and also feed forward. I just cut this table accordingly to take certain example. So this is how we manage how to control the DC. Certain parameter that we want to control, like flow rate, temperature, and also pressure. Now let's move on. Alright, let's go for the PNID diagram, which is the total overall diagram shown in the slide, whereby you can refer. If there's anything you want to ask, sure. And now let's go on with the chapter 9. Thank you.
Hi, my name is KAMALINA AZYYATI, and I will be presenting my design equipment for heat exchanger E100. Heat exchanger is an equipment used in the process to allow the heat transfer between the two streams by the two fluids without any contact or mix-up. In this plant, shell and tube heat exchanger is selected as the heat exchanger used. E100 is located at the stream before entering the reactor 1 R100. The purpose of this heat exchanger is to decrease the temperature of ethylene from 210.64 degrees C to 95 degrees C. For chemical design, the steps involved are determine the heat load, select trial value for the overall coefficient, calculate the mean temperature difference LMTD, calculate the area required, and lastly, calculate the overall coefficient and compare with the trial value. The table shows the physical properties for the two fluids involved in this heat exchanger, which are ethylene in gas phase and concentrate in liquid phase. So this is the summary for chemical design. For this design, the heat load required is 251.59 kW. The heat transfer coefficient is 191.20 watt per meter square degree C. The heat transfer area is 127.14 meter square. The tube pitch used is triangular pitch with 260 tubes. For mechanical design, the steps involved are to identify the operating and design temperature and pressure, material of construction, corrosion allowance and design stress for shell and tube side, weight load of the heat exchanger, and lastly the support design. So the table shows the summary for the mechanical design. The material construction for both shell and tube side are carbon steel, with the weight load of heat exchanger is 59.34 kN. The minimum wall thickness for the shell side is 4.78 mm and for the tube side is 2.05 mm. So this is my AutoCAD drawing for heat exchanger E100. This is shell and tube type of heat exchanger with ellipsoidal heat, solder support, and welding net for flange. The baffle type is 25% with diameter of 521.8 mm with 9 number of baffle. Then I will pass the net presenter.
Chose fixed bed reactor in order for the hydroformylation to take place because our reaction involves heterogeneous gas-solid phase flow reaction. In order to achieve higher conversion per weight of catalyst, we need to use fixed bed reactor since this FBR has better conversion than the other catalytic reactor. We use solid rhodium as our catalyst to speed up the rate of reaction because it has high reaction rate, high stability, and production of byproduct. The flow is characterized as plug flow since there are tubes in the fixed bed reactor to place the catalyst. There were several assumptions that have been made in order to design our reactor, such as the reaction occurred in steady-state condition, the process is isothermal, the reaction rate is varied for the following stated reaction, void fraction of catalyst is 50%, and the reactor is referred to as a plug flow reactor. So we will follow the calculation of plug flow reactor. And these are the steps in chemical design as shown in the slide. To summarize the chemical design, this reactor has diameter of 3.04 meter, length is 6.08 meter, and the orientation is vertical. While the design of tube is the inner diameter is 0.05 meter and 0.048 meter for the outer diameter. And the number of tube is 1,340 tubes. Since the hydroformylation reaction is an exothermic reaction, so we will provide the sufficient heat transfer in order to control and maintain the temperature of the reactor. So we need to fit an external jacket outside of the reactor in order to transfer the heat released. So to summarize the mechanical design, the design pressure is 1100.09 kilopascal and the design temperature is 104.5 degrees Celsius. Since hydroformylation reaction is an exothermic process, so we need to find the most suitable material that can withstand to high temperature, and we found that stainless steel 304 type as our most suitable material of construction, since it is the most corrosion resistant material that is commonly found in chemical industry. As our reactor is in vertical position, so we will use the skirt support as it is designed to support the vessel that is in vertical position. And here is my AutoCAD drawing for my design fixed bed reactor. Next, I will pass to our next presenter to present about his design, which is two-phase separator. Thank you.
Assalamualaikum and good morning. My name is Muhammad bin AMRAN and I'm going to present my design equipment, which is the two-phase separator V100. This is the basic diagram that shows the temperature, pressure and the molar flow of each stream in and out of the separator. The function of this separator is to separate the undesired components such as carbon monoxide, hydrogen, ethylene from the desired component, which is propanol. For the chemical design of the separator, there are several factors and parameters that we need to calculate. All of those factors and parameters are shown in the slide as follows. There are 7 parameters and factors that we need to calculate. The result of previous calculation referred by the previous flowchart. This is the data that I get. The density of each stream and the total height of the vessel, which are 2.31 meters, and the diameter of the vessel, which are 0.81 meters. By the rule of thumb, the L and D ratio of the vessel is within the acceptable range proposed by our journal. In mechanical design of our vessel, we need to calculate 10 factors and parameters such as the design temperature and pressure. All the factors and parameters are as shown in the slide as follows. As the result from previous calculation, this is the data that we get. The weight of the vessel is 6,274 Newton and the head design is spherical. The operating pressure and temperature is 30 degrees Celsius and 0.748 Newton per millimeter cube. The vessel used cylindrical skirt type of support and the diameter of each nozzle is shown as follows. This is the AutoCAD drawing of our vessel. The material of construction of our vessel is made of stainless steel, and the flanges design of our nozzle is shown in the right of the slide. The insulation is made out of fiberglass and the skirt is carbon steel.
Hello, Assalamualaikum. My name is Aziera, and now I will proceed with design of equipment for hydrogenation reactor. The type of reactor that used for hydrogenation process is a multi-tubular fixed bed reactor. This reactor consists of a large number of parallel tubes that are placed inside a cooling jacket. The arrangement of fixed bed reactor, in which the gaseous reactant flows through the tubes that contain the pack of cobalt catalyst, and the coolant are externally circulated around the tube, which act as a cooling medium. These are the steps in order to design the reactor for chemical parts. The function of this reactor is for the hydrogenation of propanol and hydrogen to produce one propanol with the help of cobalt catalyst. A few assumptions has been made, such as reversible reaction, heterogeneous system, and second-order reaction. Stoichiometry table is used to determine the concentration of reactant. Then, the volume of reactor is used by using Simpson 3/8 rule and trapezoidal rule for determining the area under the graph. The hydrogenation reactor is designed with 48.39 meter cube volume, 2.49 meter diameter, and 9.96 meter length of reactor. These are the results that obtained after the calculation has been made for designing the chemical parts of hydrogenation reactor. Next, we proceed with the mechanical design for hydrogenation reactor. These are the steps to design the mechanical parts of hydrogenation reactor. In this hydrogenation reactor, the material that we are using for the vessel, tube, and supports are stainless steel 304N, as it involves cooling water in shell side for the heat exchanger. Stainless steel 304N has excellent resistance to corrosion, availability in the market, and can withstand high operating temperature, which make it suitable to be used for this hydrogenation reactor. The reactor is in a vertical with an ellipsoidal head and has insulation that made up from mineral wool. These are the summarized AutoCAD drawing for hydrogenation reactor on this one propanol production that consists of cross-sectional of top and side view, their top, side, tube, head, and insulation view with their information. Next, we will proceed with design of distillation column by Jimmy.
Thank you, Leslie. Let's go for distillation column. Why we propose DC as our separation unit? Because of these four factors, which is high purity product, excellent vapor-liquid interface, acceptable for high loading, and also good heat and energy recovery. This is the chemical design for distillation column. As you can see, there's certain assumption that has been made before the calculation of dew point and bubble point. Then followed by volatility and the flux ratio, and also stage calculation, plate design, and last but not least, column design. In the slide as well is a partial of the table, which is the chemical design table included. Sieve tray are acceptable for this distillation column. The height and diameter of this distillation column is in optimum range, which is under 30.0. And also, the efficiency of the tray is above 51%, but can be improved by the stages, which is 29 stages. Here come with the mechanical part of the distillation column. Not so much different compared to others. Safety factor included in design, temperature and pressure, also the stress factor. Corrosion and wall thickness, total net weight can be bare by the support skirt itself, and also stress analysis and the best selection of construction material. Shown in the table is a partial also, a part of mechanical design that you can refer to. This is the AutoCAD drawing for distillation column. That's all for chapter 9, major equipment design, and we will proceed to chapter 10. Thank you.
In this chapter, we are going to present about our economic analysis of our design project. The economic review in this chapter is basically continuation of our business analysis in chapter 1, undertaken in project design 1. Assessing project profitability, including both capital expenditure and annual operating costs, is very important. Therefore, for the purpose of economic evaluation, forecast of the cost of capital, which are how much money needed for the building of a new capital project, and the production costs, which are the how much money it takes to run the chemical plant, should first be calculated. This is the bare module cost of every equipment in our plant. Every equipment have different variables such as the surface area and type of material of construction. For example, E100 and E101 have different surface area and material of construction, thus have different CBN value. The total CBN of this plant is 58,529,446 ringgit. To calculate the total capital cost investment, first, we need to identify the direct cost. Direct cost is the price that can be directly tied to the production of specific goods or services. A direct cost can be traced to the cost of object which can be service, product, or department. The total direct cost is 69,240,334 ringgit. Next, we need to identify the indirect costs. Indirect costs are costs that are not directly accountable to the cost of object, such as a particular project, facility, function, or a product. The indirect cost may be either fixed or variable. The total indirect cost of this plant is 17,500,304 ringgit. The fixed capital investment is the investment taken to fulfill a process project by building process equipment with the inclusion of auxiliaries. It covers both direct costs and indirect costs. The total capital investment is a summation of investment in fixed capital, operating capital, and startup. Thus, the total capital investment of this plant is 208,421,060 ringgit. In order to estimate the manufacturing cost, we need to process the information provided on PFD, an estimation of fixed capital investment, and estimation of the number of operators required to operate the plant. The cost of each parameter is stated in the slide as follows. In order to get a profit in a project, the life for the process must be assumed. It can be working life of the equipment or it is the time of depreciation. Usually, life of 10, 20 and 15 years are used for these purposes. For chemical processes, the operating usually greater than 10 years. In this case, we use 12 years. The cost for each parameter are shown in the slide as follows. Before we start with the non-discounted cash flow, this is our assumption. The plant startup is at year 2 and depreciation we use of 5 years MACRS. We assume the project life is 12 years and we can see the positive cash flow start at year 6. From the non-discounted profitability analysis, the payback period is 3.83 years. The cumulative cash positive is achieved at year 14, which is 366,780,069 ringgit. The rate of return investment represents the non-discounted rate at which money is made from our fixed capital investment, which are 3.2% per annum. For discounted cash flow, rate of return is at 20% per annum, which the net present value is equal to 0. The main difference between the non-discounted and discounted criteria is that we discount each of the yearly cash flow back to time 0. This concept assumes that money is worth more today than it is in the future. Then, the result from the non-discounted cumulative cash flow diagram is used to evaluate profitability.
Next, we will proceed to Chapter 11, Plant Safety and Layout. Safety of a workplace must always be updated according to the latest issue, including risk and hazard, which may cause undesired accident or fatality. It is important to identify risk and hazard for workplace safety. We must identify the safety control as what has been implemented in safety analysis. Two common acts are OSHA 1994 and Factory Machinery Act 1974, which used on petrochemical industry in Malaysia. Then, HIRAC, HAZOP, and Hazard Register is correlated to each other in order to identify the risk and hazard for the safety of plant production. And emergency response plan indirectly provide a better understanding to all operators and working personnel in the area. Plan layout is an effective physical structure in design for industrial installation. HIRAC is one of the simplest methods to analyze possible hazard available in workplace for a proper planning. Before doing HIRAC, we must identify existing risks and hazardous components and also summarize all the analysis of hazard area in the hazard register. These are our 1-propanol production of HIRAC form. For such, a welding in mechanical work activity may cause a harmful to workers. It is required for the workers to wear a proper PPE. HAZOP is a systematic way to identify some detectable hazard on workplace and propose several control by following the SOP. These are the example of HAZOP for the reactor equipment, such as the process parameter for temperature. If it is a low temperature, it may be due to the leakage or failure of instrument or compressor. This might be cause the temperature to deviate fast and will affect the reaction rate and low conversion of product. Hence, the worker may take action to install the temperature indicator and always ensure that the temperature controller is in a safe condition by doing a maintenance checkup regularly. This is our PNID after the HAZOP has been taken in action. Emergency is an unexpected situation that can give bad consequence to the organization. A quick response to the emergency is essential. For those reasons, the plant should always be prepared for the emergency. These are the procedures for on-site and off-site of emergency response plan to be followed during the threatened situation. Keep and notify the local authorities for immediate response when the situation is out of control. Several factors are considered in designing the 1-propanol facility to ensure that the proposed layout are in the highest level of safety. For this 1-propanol production, the plant is divided into processing area and non-processing area. Determination of wind direction is crucial in order the equipment to be located in the right position. In the non-processing area, to minimize the walking distance for staff working in this area, general buildings such as office, canteen, lab, control center, and recreational amenity will close to each other. Fire station and assembly area located near the exit gate. All the high-risk areas are located in the processing area with 2 exit emergency. Plant utilities and waste treatment must be placed near to the plant process in order to aid the efficiency of plant production. An area are reserved for future expansion project. That's all from us for the presentation of design project 2. Now we will proceed to the Q&A session. Thank you.